class. Okay, so they may ask you. And roll number 94, Saransh. Saransh Mittal. Saransh is
Yes,
there?
sir.
Okay. So now we will start this today's class. Okay. This today's class is very excellent example actually. Excellent example. Sometimes you will see some problem. Okay. But solving the problem, so you need to all together somebody's mic is on. Okay. So you will see some problem actually. Visually you will see some problem, but solution of that problem you need to assume something. That assumption will be very, very important. So maybe you will get a final solution in a steps, and you need to solve the problem in a steps. So in a step 1, step 2, step 3, and this will be the case in each and every research problem. So you don't see that, okay, whatever currently you have technology, like say everybody is using mobile technology. This solution is not somebody solved in a day. Okay, there will be thousands of people involved in this problem. So stepwise people have solved actually. Initially, it might have been started with communication. So how to transfer the message, that problem is solved. Then hardware, then compact, how to make the compact hardware, then how to resolve the problem of heating and cooling, then how to resolve the problem of giving the energy to this device. So now people are solving this problem step by step. So stage-wise problem solved. So exactly same problem what you can see on a screen. So this is also, if we want to solve the overall problem. Overall problem is there is a gas A. So gas A is coming in the reactor. Okay, this is packed bed catalytic reactor. So you can say tube. Okay, tubular packed bed reactor. Catalyst particles are packed. So gas A is coming in here. Say this is the length of the reactor. Length of the reactor is L, and here so A is converted to gas B. Gas A is converted to gas B, and here you will have the, so B is your product, but there will be some unreacted A also, and here you will get a mixture of A and B. Say overall conversion. So now you will be always targeting. Okay, so overall solution to this problem is, say I want to have maximum production of A. So maximum production of A. So what should be the conversion of A, final conversion of A? That can be one thing. And what should be the input flow rate? So I will get appropriate capacity of B. Conversion and quantity of B. That is what main parameter I am interested in. Conversion, overall conversion from this point to this point. What is the conversion of A? Say I am introducing 100 molecules. Say 50 molecules are A and 50 molecules of the 50% conversion. But I want 50,000 molecules, so I will be introducing say 100,000 molecules. 100,000 molecule, or I can give a longer residence time also. That residence time also will be deciding the conversion and quantity of B. That is my overall aim. But for solving this, so you need to divide this reactor into parts, because what is happening? So this A molecule is going to this catalyst particle, and again diffusing back. So B molecule is diffusing back. So A molecule is going to this catalyst particle and reacting. So reacting, and B is diffusing back. So slowly, this conversion is increasing. Conversion of B is concentration of B will increase, and concentration of A is increasing. Okay, so as far as all the problem which we have solved, so we have solved so many problems where bulk of the fluid concentration was constant. But here what is happening? So bulk of the fluid. So this A molecule is going in here, reacting, and diffusing back. B molecule is diffusing back. So here you can expect, so here say mole fraction of A is 1. So here you can expect say mole fraction of A will be 0.95 and mole fraction of B will be a 0.05. If you move down the line, so say XA will be a 0.9 and XB will be a 0.1. If you move down the line, so XA will be a 0.8 and XB will be a 0.2. Anyway, it will be a binary system only. So if you move the line down the line here say XA will be a 0.5 and XB will be a 0.5, 50% conversion. So that depends upon length, how much length you are giving, temperature, pressure, everything, catalyst, everything that plays so many roles. So that bulk of the concentration is varying actually, bulk of the concentration is varying. So to solve this problem, so this problem is divided into two stages. Initially, we will discuss what will be the rate of mass transfer from individual catalyst. Okay, individual catalyst. And assuming, so this radially, if say this is say radially, the concentration of A and B remains constant. Concentration of A and B remains constant. That you can take it as a XA0 and XB0, and that is called as a bulk local concentration. So local concentration is constant. So here we'll assume a local concentration of A and B is constant, and we'll derive the concentration profile and flux profile around this catalyst particle. Around this catalyst particle, if we know flux around this catalyst particle, then again, but I am interested in what is the conversion of A to B from here to here. So at the smaller delta L, I will assume that there is no change in a concentration, smaller delta L, and integrate, and then we'll calculate, we'll take a mass flux in second stage. Initially, in first stage, whatever mass flux we have, so using that flux, so we'll be assuming that quasi steady state in a L direction, quasi steady state in L direction, and integrate this mass flux over 0 to length, and you will get a final concentration of A and B. So here for this problem, we will be solving for stage 1 only. Stage 1 means around this particle, what will be the concentration profile and flux profile. So, and same problem you can extrapolate to get this final concentration of A and B. Okay, that is what very important problem. Very being a chemical engineer, this is very exciting problem also. So diffusivity of A and B is diffusivity, DAB is given, diffusivity of A and B, and delta is a gas film thickness around this catalyst particle. So delta is a gas film thickness around this catalyst particle, through which it is expected that overall resistance to mass transfer exists. There is no resistance to mass transfer in the bulk of the fluid. So overall resistance to mass transfer assumed to be exist in a thin film surrounding this catalyst particle, which with thin film is of thickness delta. Okay, this delta, so you can use interface mass transfer to get the approximate value of delta for corresponding A and B and catalyst particle. It depends upon three: A, B, catalyst particle, as well as temperature, pressure, everything will. So you can go in literature and get the value of delta. So that will be gas film, and it is assumed. It is assumed that overall resistance to mass transfer will be in this film delta only. So this delta is around this gas film. So visually observing the problem and what is actually you are doing in the problem, that is altogether different. Altogether different. What we are doing is we are doing a mass transfer around this catalyst particle. That information can be extrapolated and get the conversion here. If you know all the catalyst particle and how concentration is changing, that will give you overall resistance to mass transfer. But here we are concentrating this particle. So this is our reactor. This is our reactor. Now you concentrate. Okay, concentrate 100%. What we are doing exactly? This is our reactor, and what exactly we are doing is, say this is a spherical, okay, sphere with a coating of catalyst material. So some inert material is there. So catalytic particle is coated, or you can call it as a catalytic particle. This is my particle. So I'm interested in this only at in stage 1. So I will estimate the concentration profile and flux profile around this particle only. Then I will integrate overall length. Then I will integrate overall length considering variation of concentration and everything. Then I will get overall concentration. But in stage 1, I am giving concentration to this one catalyst particle only, and want to study a mass transfer. And generally, we have also discussed this film delta thickness of the film will be very smaller as compared to diameter of the particle. So this is hypothetical gas film where we are assuming that overall resistance to mass transfer exists. So overall resistance to mass transfer exists. So this is one catalyst particle. This is the catalyst particle. So this is, so we are doing overall this, whatever derivation we are doing, rate of mass transfer or flux and concentration profile, we are for individual particle. This is stage 1 only. Stage 1. So if you enlarge this, so this is the enlargement of same particle. If you enlarge this particle, so this is the level of film thickness as compared to diameter of the particle. So if you go in catalysis, so catalyst itself will have a diameter something around in micron also, and sometime in mm also. So, but whatever be this film we are assuming through which overall resistance to mass transfer exists, so that will be very small as compared to this diameter. So this diameter, this is to assume this, you can assume that okay. So we have Earth and we have an atmospheric layer around the Earth. So if you look at this atmospheric layer from the sun, from the moon, so it looks a spherical, okay, around all Earth is there. But if I am standing here, I could not feel the sphericity of Earth as well as the sphericity of atmospheric layer. It is exactly similar thing. So if this thickness is very small, we can neglect the sphericity of this layer. Okay, this is the gas film and this is the catalyst surface. This is the gas film and this is the catalyst surface, and this is the bulk of the gas. This gas film thickness is very small as compared to diameter. So if you enlarge this, so you can neglect the curvature. You can neglect the curvature and assume a flat surface, two flat surface between which we are studying the mass transfer. Two flat surface between which we are studying the mass transfer. This is when we are enlarged. So this again further enlarging. So this is this surface. This is the catalyst surface, and this is the thickness of the gas film. This is the thickness of the gas film. So why we are doing everything? So instead of using a spherical coordinate system, we can use a Cartesian coordinate system. So instead of using spherical coordinate system, you can use Cartesian coordinate system, and it will be always easy to use a Cartesian coordinate system and solve mathematically in Cartesian coordinate system. So this problem can be solved using Cartesian coordinate system if I am assuming flat catalyst surface and which is covered with some stagnant gas film. This is the stagnant gas film of A and B only, through which mass is transferring. What is happening? Here bulk of fluid is there. From here A is coming in and it is diffusing that. Here there is no resistance to mass transfer. It is freely moving here. There is no resistance to mass transfer. Resistance to mass transfer, overall resistance to mass transfer is in this film only. So A is diffusing or convective, A is moving in here by molecular transport and convective transport, reaching this surface and reacting. B is forming. Now here concentration of B is very small, 0 say. Initially it will be 0. So here concentration of B will be larger. So because of this concentration gradient, B will move back. Okay, B will move back. So there will be a flux of A and flux of B will be in opposite direction. A is moving from bulk of the fluid to the catalyst surface, and B will be moving from catalyst surface to the bulk of the fluid. So slowly, as you move with a dip from catalyst particle to catalyst particle and length of the reactor, so concentration of B will keep on increasing and concentration of A is keep on decreasing. But for local concentration, we can assume bulk of the fluid have a constant concentration. Say you can consider XA0 and XB0. So assuming this, so this can be solved. So this is the age of the hypotheticals. So you can see this is hypothetical. So everywhere you will see that in reaction engineering also this fundamental come, in mass transfer also when you are discussing two-film theory, and there also this is not the actual gas film, this is a hypothetical gas film, but this is very important fundamentals in mass transfer and kinetics, because based on this we are trying to catch up all the physics of the problem in mathematical modeling. We are trying to define mathematical models for various physical processes which is happening in chemical engineering. So that hypothesis is also very important. So stagnant film is there. So A is diffusing from bulk of the fluid through this stagnant film, and it is reaching here, and after this is catalytic surface, two molecules of A is combining to form a B molecule, and it is irreversible and instantaneous. Instantaneous means as soon as A reaching here, it is converted to B. That is called as an instantaneous, very fast reaction. So what will be the concentration of A here at the surface? Its reaction is instantaneous. The roll number 101, Ritendra. Roll number 101, Ritendra Singh.
Sir. Hello.
Tell me, what will be the concentration of A at the surface? Expected concentration profile for A.
Hello. Hello.
Tell me.
Yes, sir.
Expected concentration profile for A. What will be the concentration profile at the surface? A at the surface. Expected.
Sir, 0.
0. Why?
Sir, because there is no a layer present there. Means
There is no,
there is no
there, but A is coming in here, no?
sir, but it is not. It is coming from. Sir, the reaction is irreversible and instantaneous.
That is most importantly instantaneous. The reaction is very fast. The reaction is very fast. Means as soon as A reaches here, it will be converted to B. So certainly concentration of A at the surface will be 0. Concentration of B at the surface will be maximum. Mole fraction of B at the surface will be 1. And as we move in this direction, slowly concentration of B will decrease and will reaches the bulk of the concentration. Here, will reaches the bulk of the concentration, and A, slowly concentration of A will increase and reaches the bulk of the concentration A here. So this is, say, if we plot XA and XB, so this is expected concentration profile. This is expected concentration profile. Say this is 0 and say this is 1. This is 0 and this is 1. So at this surface, XA will be equals to 0 and XB equals to 1. Slowly, XB will be decreasing, XB will be decreasing, XB will be decreasing, and here XB will be the smallest. Say, for example, XA, here XB0 is 0.2, so XA0 will be, say, 0.8. XA0 will be 0.8. So this is what expected concentration profile is there. And you don't get confused. Okay, don't get confused. This is z equals to delta. So here, say here is my origin. This is what my origin. So I can select anywhere. Cartesian coordinate system. I have 8 options. So here I have selected the origin, and this is my z direction. Flux is in z direction. Now, if you compare with actual problem, this is my r direction. This is my r direction. R is compared with a z in Cartesian coordinate system because thickness is very, very small. Now you don't get confused with this reactor and this figure. Okay, this is what expectation, and this is because this also looks a rectangle, and this is what many times happen in examination. Okay, people will think that this is the approximation of this reactor. This is not approximation of this reactor. This is actually approximation of the surface of this catalyst particle, and thin layer around that. So this is the surface of this catalyst particle, and this is the thin layer around that. This is what many times people will get confused with these two figures which is given in a book. But this is not the approximation of this reactor. This is the approximation of one catalyst particle and a thin layer around this. So using which what we will get? You will get a local rate of conversion of A to B. So if I have a local rate of conversion of A to B, and say if I know how concentration is changing, so I can assume a thin thickness in this L direction and assume quasi steady state and then integrate over L. So I will get an overall rate of conversion of A to B. Okay, then so but we are doing only local rate here. We are not doing overall rate. That you can do exactly similar way how we have done quasi steady state for varying a moving boundary problem. Okay, moving boundary problem, but this is here it is not a moving boundary problem. Here concentration is changing. Concentration is changing with the length. To account that, you can assume a quasi steady state for L. Quasi steady state for L. You cannot call it as a quasi steady state. It will be always with us time. During you can assume a small thickness L and then get a local rate of conversion integrated over this L and get the overall rate of conversion of A to B using this actually. So and this will be a flux at every particle, then surface area at every particle, and sum it over from 0 to L. So you will get a overall rate of conversion of A to B. That will be stage 2. But here we will be discussing stage 1 only. Stage 2 you can try at home how to get the overall rate of conversion of A to B. If say what will be the information you will be needing? You will be needing the information, some particular concentration, everything, what can be the boundary condition, how to assume small delta length and sum it over 0 to length. So here, but we are doing a local rate of conversion of A to B. So this is very, very important. So this is not the approximation. This is not the approximation of this whole reactor. This is the approximation of this catalyst particle. This is the catalyst surface of this catalyst particle and the thin layer around this catalyst surface. So this is enlarged view of this, and as this thickness of this film is very, this delta is small as compared to diameter of the catalyst particle. So I can neglect the curvature of this catalyst particle for study and use the Cartesian coordinate system. And here this is my origin and I am considering this is my Z direction. This is my Z direction. So just positive direction of flux of A. So because I am interested in flux of A, so this flux of A, that to match with this is my origin and this is my Z direction. So now here Z direction is similar to R direction. Z is similar to R direction and X is similar to theta and Y is similar to phi. Okay, Y is similar to phi. So in which direction there will be variation in concentration, overall variation in concentration. Roll number 2, Sonone, Rutuja Sonone, roll number 102.
Yes, sir.
So
Sir, I didn't
variation in concentration. Yeah.
Sir?
Yeah. So in which direction you are expecting variation in concentration? X, Y, Z.
Sir, in
Sir, in
uh,
sir,
Z direction, sir.
Z direction only. Why there is no variation of concentration in X and Y?
Sir, the reaction. Sir, just a equal.
Yeah, roll number 103.
Yes, sir.
Why there is no variation of concentration in X and Y direction? Here X is similar to.
Sir, in X direction, we neglect the end effects,
Okay.
and in Y direction, like there is no variation. No, it's symmetrical in Y direction.
How about X direction? What is
Sir, in X
equivalent
direction,
XYZ direction for this Cartesian coordinate to the actual coordinate system? Actual coordinate system will be a spherical coordinate system.
yes,
Z
sir.
is equivalent to R direction. What will be X equivalent to?
Z is equivalent to R direction, then X will be equivalent to the at least theta direction.
Theta direction, and Y will be equivalent to
The alpha direction, the
phi direction.
phi direction.
So why there is no change in concentration in theta and phi direction?
Sir, they are symmetrical.
Yeah. So why there is no variation of concentration in X and Y direction?
Because they are symmetrical. Okay, sir, got it.
Because
The analogy.
because problem is symmetric around X and Y. So this is
Yes.
assumption. So this why we are converting this spherical problem to Cartesian coordinate system. It's very simple because Cartesian coordinate system is easy to handle, and that is very good logical assumption. This thickness is very small. I have given an example also. Even though this Earth is spherical and your climate is spherical, but you will never consider the sphericity of this Earth while designing the building. You are designing the building, say our classroom complex is designed. That time we have not considered the sphericity of Earth and climate. We have considered it as a flat. Because the dimensions, okay, diameter of the Earth is very large as compared to the area we are considering. So same thing here, thickness is very small as compared to diameter of the particle, and it is not varying in X and Y direction. Hence, because a problem is symmetric around X and Y direction. Original problem is symmetric around theta and phi direction. So what will be the dimensions of differential shell, Sanjay? 107, Sanjay.
Hello, sir.
Tell me.
Yes, sir.
What are
Delta
the
Z, X
dimensions
and
of
Y,
the
sir.
different? Yeah, delta
Delta Z, X and Y, sir.
X and Y. So you can call it
Yes,
as a
sir.
surface area. You can call
Yes,
it
sir.
as
Yes,
a
sir.
X into Y is the surface area into delta Z. So now you can take a differential shell. So you can take a differential shell in this direction. So there will be flux in Z direction only. And this, so you always, that is what I am telling, that don't confuse. This is also look a rectangular, even though it is not a rectangular. This is cylinder. Front view of a cylinder looks a rectangular. This is also rectangular. So this is not an approximation of this complete reactor. This is the approximation of one particle. This you should remember. So it will be giving a local rate of conversion. Then using this local rate and the local steady state, so you can extrapolate this information, integrate over overall length, and then you will get overall rate of conversion. Okay. So here, so this will be my dimensions of differential shell. So this differential shell will be delta Z, X and Y. Surface area, say X into Y is the surface area. So this will be the rate of this will be a flux of A coming in my differential shell, flux of A going out of my differential shell. So how to get rate? Rate will be a flux multiplied by surface area. That is what I told in first class also. First class we have started this transport phenomena with a definition of flux. That is what we are observing now also. Now we are towards the end of the transport phenomena. Still we are with flux. So flux is very, very important property in transport phenomena. In fact, it is very, very important property in heat transfer, mass transfer, and momentum transfer. Flux, concentration profile, flux profile, concentration profile. Almost 80% problem will be solved in all these three areas. So this flux multiplied by surface area will give me a rate of A coming in this differential shell. Flux multiplied by surface area will give me a rate of A going out plus generation and consumption. What will be generation and consumption in this differential shell? Roll number 8. What will be generation and consumption of A in this differential shell? Roll number 9109, Shashank.
Yes, sir.
What will be generation and consumption of A in this differential cell?
Sir, A will be consumed and generation of A is not there.
Okay,
So first
in this differential shell, there is no generation and consumption of A.
yes, sir.
Is it so? In this,
Yes, sir.
where it is consuming at the boundary.
At the down, yes, sir.
That we will
At the-
use as a boundary condition. That we will use as a boundary condition because this information, this instantaneously fast means here I am seeing A will be equals to 0. That is boundary condition. But in this differential shell, there is no generation and consumption of A. So you will get very simple rate of mass coming in, rate of mass going out plus production of A, that will be equals to 0. Now this is what I am divided by S into delta Z. S into delta Z tends to 0. Delta Z tends to 0. So what you will get? You will get a d by dz of NAZ, that is equals to 0. It means that NAZ is constant. NAZ is constant in Z direction. NAZ is not varying. D by dz of NAZ equals to 0. There is no variation of flux. So whatever be the A coming at the top surface, that's at same rate it will be consumed, or whatever be the rate of consumption of A, with that rate only A will be coming in that differential shell. So now NAZ, how to get NAZ? Roll number 110, Tanmay.
Yes, sir. So,
How to get NAZ?
yes, sir. Like we have the binary system. So,
Can you be loud, little loud? Your mic is not working properly, not audible.
hello, sir. Hello, sir.
Tell me.
So we have A and B. So we have binary system. So we can.
No, your mic is not working properly. 111.
Hello, sir.
Your mic is not working. Roll number 111, Vipasvi.
Hello, sir.
Yes, sir.
How to get NAZ?
Sir, we can use the equation of combined flux.
Very good, very good. So this is the difference actually. So when we are studying a shell balance for momentum transfer and heat transfer, that time based on situation, we might have been used only conduction or molecular flux, or sometime combined based on situation. But in mass transfer, all the time we will be using combined flux only. Why it is so? Vipasvi, roll number 111.
Hello? Sir,
Why
am I
we
audible?
yeah, you are audible. Why we will be using combined mass flux all the time in mass transfer?
Uh, sir,
Uh-huh.
sir,
Because
because there
tell
are
me.
two species. It's a binary system.
No, mass transfer itself is a molecular transfer. Molecule is moving from one place to another place, which is nothing but the bulk motion.
Yes, sir.
So it is very difficult to differentiate convective mass flux and molecular mass flux for mass transfer. conductive flux and convective flux, it is very difficult to differentiate. Every time there will be a bulk motion, only a magnitude of bulk motion which will be characterized by velocity, that velocity will be smaller or larger. If smaller, then we will be categorized that into a molecular flux. If it is that larger, then we will be categorized into molecular convective flux. But there is no case that without molecular motion, mass is transferring. Mass transfer itself another name of molecular transport. Okay, that is why we will be using combined flux. So using this combined flux, definition of the combined flux for binary equation, Na will be equals to C dAV dXA by dZ. So you can get in Z direction. You can get in Z direction. This will be in Z direction. So what will be NAZ and NBZ? What is the relation between, what is NBZ equals to? Roll number 112.
Yes, sir. Hello,
What
sir.
is the relation between NAZ and NBZ?
Sir, NABZ equals to minus 1 by 2 of NAZ.
Yeah,
Trigonometrical.
because two molecules of A is coming in and one molecules of B is going in negative direction. So if it is coming at a 20 molecules per unit area per second coming to the surface, 20 molecules of A, 20 molecules are molecules of A coming to the surface of the catalyst per unit time, say per second, per area, per meter square. So how many molecules are going back? 10 molecules. Because two molecules are combining to form the B. So 10 molecules will be moving in opposite direction per unit time, per unit area. So that is why, so this reaction is 2A gives B. So which will gives NBZ equals to half of NAZ. Okay, NBZ equals to half of NAZ. Now substituting this and rearranging the equation. So rearranging the equation, this is what we will get NAZ, combined flux, in terms of combined flux. This is not just a fixed law. This is the combination of fixed molecular flux by fixed law as well as convective flux. And in convective flux also, you will have some information from reaction, because two molecules of A reacting to form one molecules of B. So flux of B will expected to be half of A in opposite direction. Opposite direction means negative sign. So this will be a half of NBZ will be a opposite of NAZ and half. So that is what, substituting this information. So we will be getting this NAZ. This is the NAZ which is correlating concentration with respect to flux. This is the concentration with respect to flux. Now substituting this information in shell balance equation. This is what equation we will get. C is the total concentration assumed to be constant. So say total concentration depends upon pressure and temperature. So pressure and temperature is not changing. So it is not given. If that is also changing, so we need to assume that also here. Say assuming that total concentration is kept constant, as well as this diffusivity is also kept constant. So this will be the equation. Now integrate this equation twice. So, and then you will be getting two boundary conditions. You will be needing two boundary conditions to solve. You will be getting two constant. So first integration will be with respect to this dz. Another integration will be with respect to this dz. So you will be getting two constant. To solve for this two constant, you will be needing two constant. So what are the two constants available? Roll number 113.
Sir, we have it z equal to 0 and z equal to delta. We get both boundary conditions.
Yeah. What is at z equals to 0? Z equals to 0.
Z equal to 0, we have XA naught. Like XA value will be XA naught.
Yeah. That will be bulk concentration, local bulk concentration. XA 0 at z equals to delta.
At z equal to, we have XA is 0. We don't
XA
have XA because it gets converted to
instantaneously
B.
Instantaneously fast reaction. So this is what expected. So this is the first integration. So first integration, okay, this ln 1 minus xa, and this 2 is coming here, 1 by 2 is there. So divided by 1 by minus 1 by 2, that will give you minus 2 equals to C1Z plus C2. Okay. First integration will be C1 and second integration will be C1Z plus C2. So this is what this thing will be there. So now I want to, because this logarithm is there, so it will be always better to handle linear equation so as to estimate the concentration, this C1 and C2. So what is trick we are using in all the problem? Roll number 115, Pathak.
Hello?
Yeah.
I'm audible, sir?
So
Yes, sir.
how to eliminate this land?
So by applying boundary conditions at like Z
No.
equals
How to eliminate this land first of all? This land means logarithmic term.
yes, sir.
Why we are eliminating land? Because it is easy to handle a simplified mathematics. So
Yes, sir.
everybody like a simple mathematics.
Yes,
Complex mathematics means multiple solution.
Yes, sir. So by applying logarithmic on both the sides.
Yeah, very good. So instead of this linear constant, we will be using logarithmic constant.
Yes, sir.
So say C1 equals to so some here also I have constant. So this C1 equals to 2 ln K1 and C2 equals to 2 ln K2. So this is also constant, this is also constant. Okay. So just to eliminate this constant also and this logarithm also, this is assumed. This is also constant. Certainly K1 is constant, 2 ln K1 is constant, which is equals to C1. So C1 equals to 2 ln K1. So this is what you need to do. Simplifying mathematics all the time. You should be you should not target adding the complexity in mathematics. So if you want to solve the problem, all the time try to simplify the problem as simple as possible as far as mathematics is concerned. So this is one way. Here I have 2 and here I have ln. I want to eliminate this 2. Then C1 is assumed to be 2 ln K1 and C2 is assumed to be 2 ln K2. Now rearranging the equation. Rearranging the equation. So what I will get? 1 minus half xa, that is equals to K1 raised to Z and K2 raised to Z. K1 and K2 are constant, 2 constant and 2 boundary conditions. So what is this boundary condition? Both the type of boundary condition is concentration is mentioned even at the surface. Concentration at the surface can be specified. This is a type of boundary condition. So here I have given a concentration bulk of the A. So bulk of the concentration in bulk of the fluid is Xa0, and as here reaction is very fast, so at Z equals to delta, Xa equals to 0. So these are the two boundary conditions. So now get me the value of K1 and K2 and rearrange the equation. So substitute this boundary condition here. At Z equals to 0, Xa equals to Xa0, and at Z equals to delta, Xa equals to 0. So substituting this, get me the value of K1 and K2. Roll number 116, Abhinit. Roll number 117, Shashwat. Shashwat. Hundred and 19, Tarun Sai.
Hello.
Yeah, what will be the value of K1?
Sir, the value of K1 will be
1 minus x naught a by 2 whole power minus 1 by delta. Sir.
Okay, and what will be the value of K2?
Sir, the value of K2 will be just a second, sir. 1 minus x naught a by 2. Sir.
Okay. Sir, we can use combined binary clause. Okay, everybody is getting this equation. Everybody is getting this equation. Yes, yes, yes. Very good. So many people are getting this equation. Now you should be expert in handling mathematics. That is what expected. Okay. So you should be, anyway, you are better than me in mathematics. So that you should work. Okay. So K2 will be equals to 1 upon, this is what. So everybody is getting this equation K1 and K2. Here roll number 119. Tarun,
Yes, sir.
you got this K1 and K2?
Yes, sir. I got the both
Okay.
the value.
Okay, very good. So if you substitute K1 and K2 and rearrange the equation so that you will get a concentration profile. Substitute this equation K1 and K2 and get the concentration profile. So this is what concentration profile you are expecting actually. So 1 upon this 1 minus half xa0 raised to 1 upon z divided by delta. So at given value of z, so you can get the value of xa. This is what concentration profile. Now you can get a flux profile. How to get a flux profile? So if you go back, okay, if you go back, so here say NAZ can be, so this NAZ is this. So this will be, okay, what this will be equals to C1. Okay, this is NAZ. NAZ equals to minus C DAB 1 upon 1 minus half XA dxa by dz. And what is this equals to? If I integrate just once, this will be equals to C1. And that C1 equals to 2 ln K1. So now I have K1. 2 ln K1 will be equals to C1. C1 multiplied by capital C into DAB minus. That will give me NAZ. Okay. So this is what we are doing in all the problems. This is K1 and K2. So this is what NAZ is there. So this you can see, this is what 2 ln K1. This is 2 ln K1. This whatever 1 upon 1 minus xa dxa by dz will be equals to 2 ln K1. And if I can estimate that at z equals to 0. Anyway, that is not changing with respect to z. So you can estimate at z equals to 0 or anything and get, so this is what I was telling. This 1 upon 1 minus half xa dxa by dz will be equals to C1. That will be equals to minus 2 ln K1. Minus 2 ln K1. Substituting it here. So what I will get? This is K1. This K1 here. And 2 ln K1 is C1. And C1 into this will be NAZ. So this is what a flux profile is there. Flux profile will be equals to 2C DAB divided by delta ln 1 upon 1 minus xa0. This is why xa0 at z equals to 0. So this can calculate xa also. It will not change actually. It will not this xa0. So this is at z equals to 0. Flux is constant. Flux is constant. So this is at xa0. This will give you local flux. Local flux means at one catalyst particle. Flux at one catalyst particle, that depends upon local concentration. And this local concentration is changing with the length of the reactor. If you monitor that variation in concentration and catch that variation in concentration, this multiplied by surface area will give you local rate of mass transfer. And that can be integrated over length to get an overall rate of mass transfer, and you will get a conversion at the end. So using that, so this is the local rate of conversion of A to B. This is, so we are not solving that problem completely. This is just a one stage of the problem. One stage of the problem where we got a local rate of conversion of A to B. So this is clear with everybody? Anybody has any difficulty in this concentration and flux profile? So now this is a case number 2. Same problem. This is my concentration profile. This is my flux profile. What was the situation? The reaction was very, very fast. Here reaction is very, very fast. Reaction is very, very fast means whether it is controlled by mass transfer or kinetics. Here roll number 81. Roll number 81. Karthik Reddy. Yeah. In this case, reaction was very, very fast. So whether it will be controlled by mass transfer, overall design will be controlled by mass transfer or kinetics.
Mass transfer.
Yeah. If reaction is fast means controlling parameter is mass transfer. That is why you can see that there is no kinetic parameter in concentration profile also. There is no kinetic parameter in flux profile also. Because reaction is already very, very fast. So overall design will be controlled by mass transfer. Because overall controlling parameter is mass transfer. This is the case 1. Now second one, if reaction is not fast, but will be given by this equation. This will be, so this is not exactly kinetic constant. You can correlate this kinetic constant. This is instead of rate, I am discussing flux. Okay, rate of reaction, I am discussing flux. So here also instead of a pure kinetic constant which you are discussing reaction engineering, it will be kinetic constant per unit area divided by area. So instead of here rate, I will be discussing flux, because here more as first class also I am telling flux, here also I am telling flux. So kinetics also we have modified according to flux. Instead of rate, we will be discussing flux. NAZ equals to K1 double dash C. That will be equals to K1 double dash. This is total concentration into XA. Total concentration into XA, that will be NAZ. That will be NAZ at X equals to delta. This reaction is happening at the surface. At the surface, this is my flux value is there. Flux value which is controlled by kinetics using this equation. So how to handle the problem? Problem handling will be exactly similar. Only boundary condition will change. So exactly same concentration profile will be getting. So what will be boundary condition in this case? So for this case, what will be boundary condition? Ishwari, 83, roll number 83, Ishwari. Roll number 84. Roll number 85.
Yes, sir.
Yeah, Karthik. What will be boundary condition for this case?
Sir, now it would be same for z is equal to 0 as in the previous case, but now for z is equal to delta, we will have change. Like it would be flux upon rate constant into concentration.
Yeah, XA, you can say XA will be equals to, at X equals to delta, XA will be equals to NAZ divided by K1 double dash C. Okay, this will be the boundary condition. Okay, so what will be boundary condition? So these are two boundary conditions. First will be a concentration is mentioned at the surface, and second will be the concentration is given by some kinetic reaction. Okay, this reaction here, it is not a first order reaction, it can be anything. Here it is first order, so it's fine actually. So at Z equals to 0, XA equals to XA0, and at Z equals to delta, XA will be equals to NAZ K double dash C. So now get the value of K1 and K2, substitute here. and get the concentration profile and flux profile. Get the value of K1 and K2. Substituting this boundary condition at Z equals to 0. If you put Z equals to 0, XA equals to XA0. So K2 will be equals to 1 minus half XA0. K2 will be equals to 1 minus half XA0. Now at Z equals to delta, not K2, K2, K1 into K2, K1 into K2, and accordingly you can get K2. Substitute this delta, two equations are there. Here on number 86, Prashant.
Yes, sir.
What is the value of K1?
Sir, K1 equal to 1 minus NAZ by 2 K1 double dash C divided by 1 minus half XA naught by 1 minus XA naught by 2 whole to the power 1 whole to the power 1 by delta.
Okay, and what is K2 equals to?
And sir, K2 equal to 1 minus XA naught by 2.
1 minus XA naught by 2.
Yes.
So substituting this boundary condition, K2 will be equals to 1 minus XA naught by 2 and K1 will be equals to 1 minus half NAZ divided by K1 double dash C divided by 1 minus XA naught whole raised to 1 upon delta. Now substitute this K1 and K2 here and get the concentration profile. Everybody is getting this constant K1 and K2, value of K1 and K2. You can write in chat box. Yeah, very good. Anybody not getting this K1 and K2 also can discuss. K1 and K2. So just give attention to announcement. There will be a compensatory class tomorrow at 11 o'clock. Take that class. We'll be completing our syllabus in Monday's class. So from Tuesday we can start the Viva as per availability. Okay, so tomorrow at 11 o'clock we'll have a lecture, one lecture. So after substituting this K1 and K2, this will be my concentration profile. Okay, this is my concentration profile. So 1 minus half XA equals to 1 upon 1 minus half NAZ divided by K1 double dash C raised to Z divided by delta 1 minus half XA0 1 minus delta. Now you can get a flux profile. Flux profile. So flux can be correlated with this. Again, same thing. This is flux. Flux will be same. Flux is same, and this will be equals to. So this you can calculate using this also at any value. Okay, at any value dxa by dz at z equals to 0. Or what you can do is this is half 1 minus half xa dxa by dz, that is equals to c1, that is equals to ln k1. Substitute k1. This is k1. Okay, this is k1. 2 ln k1 equals to c1, and this is c1 that multiplied by capital C and dAB. That will give you NAZ. So this will be my flux profile. Okay, this is my flux profile when I don't have kinetics very fast. This is not fast, then I will get this flux profile. So rearrange, use the value of K1, or can differentiate this and use at Z equals to 0. Z equals to 0. So you will be getting same concentration profile. So dxa by dz. Differentiate with respect to Z, substitute it here, and you will be getting same concentration profile. You are expected to get same concentration profile. If you differentiate this equation with respect to Z and substitute it here, so you will be getting same concentration profile. Everybody is getting this concentration profile. Roll number 88, Pratish.
Yes, sir.
So are you getting this concentration profile and flux profile?
Yes, sir.
Everybody is getting this concentration flux profile. Specifically, now we are onto flux profile. If you are getting, you can write in chat box. Okay, people are getting. So any difficulty in this concentration profile and flux profile? Now, most importantly, now you can see we have specialized case. This is for any reaction with rate constant K1. And first case was a specialized case one when K1 is very, very large. Reaction was very, very fast. So reaction was very, very fast. So this is again local rate of conversion of this is I am repeating so many times. Local rate of conversion of A to B. This is giving me local rate of conversion of A to B, because you should not get confused. It is not giving me a rate of conversion of at the end. Okay, this is local rate of conversion of A to B. So what is this? This is case 1. This is special case. When the reaction is very, very small. This is generalized case. Okay, this is generalized case when you will have some rate constant of reaction. So can we get this special case from the generalized case? Anybody in a class? Can we get this case 1 from case 2? Adding the assumptions here. Adding the assumption here in case 2, can we reduce this equation to this equation? Anybody in the class? What is the assumption? Yeah.
Sir, if the reaction is instantaneous, then K1 will be very high. So we can assume
K1 will be very, very large.
So 1 by infinity will actually become 0.
So, but directly you can put this 1 by infinity equals to 0 here.
So we can use some sort of expansion. But
say K1 is very, very large. What will be the value of NAZ? NAZ is related to K1 double dash. NAZ will be equals to K1 double dash C into XA. If K1 is very, very large, certainly NAZ will be very, very large. Infinity divided by infinity will not be a 0. So K1 is very, very large as compared to. So K1 is very large as compared to which parameter we are comparing. So K1 is representing kinetics. K1 is representing kinetics. So kinetics is large as compared to mass transfer. So which is the parameter which is representing mass transfer?
Surplus.
Yeah?
NAZ.
No, NAZ, not NAZ. It will be diffusivity. So K1 is very large as compared to DAB, instantaneously fast reaction. If say 10 molecules are coming and it is reacting 10 molecules within a second, so we can call it as an instantaneously fast reaction. But say 100 molecules are coming and 10 molecules are reacting, then that is not an instantaneously fast reaction. Same, 10 molecules are only reacting. So it is compared to mass transfer, and that transport depends upon DAB, not NAZ. And this NAZ is also related to K1 double dash. NAZ equals to, in fact, K1 double dash C into XA. If K1 double dash is larger, NAZ will be larger. So K1 double dash is larger as compared to DAB in this case. In this case, K1 double dash is not larger as compared to NAZ. So this is what happens sometime while taking the assumption. We'll take assumption, correct assumption, but wrong interpretation actually. That should not be there. If directly you take NA and write here K1 double dash is very, very large, add 1 upon larger term. So 1 upon infinity will be equals to 0, and you will get directly this equation. Because K1 double dash is very, very large. So NAZ divided by K1 double dash C, that equals to 0. And you will get directly this equation, but that is altogether wrong fundamentally. If K1 double dash is large, NAZ is related to K1 double dash. NAZ will be equals to K1 double dash. So in fact, this is equals to XA. This is XA. If K1 double dash is larger, NAZ will be also larger. So that cannot be 0. So this is K1 double dash is larger as compared to DAB. Then we should get this equation. So that is what the most of the time your assumption is correct. K1 double dash is large. You will get correct equation, but actually your interpretation will be wrong. Okay, interpretation is wrong. K1 double dash is not larger as compared to NAZ. K1 double dash is larger as compared to DAB. Now, how to get this equation, Nikita?
So we can use some form of expansion for the Ln term.
Yeah, certainly you need to use expansion. So this is very simple actually. Use this expansion. So first you expand this numerator and denominator. Okay, you expand numerator and denominator. Then this ln this plus this, you can write like this. And for ln x numerator, you can use ln x will be equals to 1 minus x, and neglecting all higher order terms. Neglecting all higher order terms, substitute that. Rearrange the equation. You rearrange the equation. So what I'm saying? So you should be able to get this equation. Okay. So this is expansion. Initially, this is same actually. Okay. Ln 1 upon 1 minus x plus tan 1 minus half this thing. Okay. Ln a divided by b will be equals to ln, this is ln a plus ln 1 upon b. Say you can think this is a and this is b. Ln a divided by b will be equals to so this will be ln b plus ln 1 upon a. 1 upon ln a plus ln upon 1 upon b. Now you can use this expansion formula for this. So that will be equals to minus, this will be x minus 1, neglecting all higher order term. This will be equals to minus half NAZ K1 double dash C. Okay. Now you can see this C will get cancelled, this 2 will get cancelled, and this will be a 2 will get cancelled. Rearranging this equation, so this NAZ can taken to this side, and what will be 1 plus 1 upon, this will be 1 plus DAB divided by K double dash. So this is what equation I will get. Everybody is getting this equation? Nikita, are you getting this equation?
Yes, I am doing the.
Now here I can say as in this equation, K is very, very large as compared to DAB. K is very, very large as compared to DAB. This denominator will be equals to 1. This denominator will be equals to 1, and hence, so as K is very, very large as compared to DAB, K is very, very large as compared to DAB. So this DAB divided by K1 double dash delta, that will be equals to 0. Hence, this will be equals to 2C DAB delta ln 1 upon 1 minus XA0. And this is dimensionless quantity actually. This is dimensionless quantity, and this is 1 upon Damkohler number. Damkohler number, I think you might have studied or you are going to study in kinetics. So this is representing Damkohler number will be a ratio of kinetic constant to mass transfer constant. So when there is a simultaneous mass transfer and kinetics is going on, that time Damkohler number will be used. Okay, so hence we can get this for K double dash is very, very large as compared to DAB. So this is Damkohler number, which is the ratio of reaction rate to a convective mass transfer. Okay, not convective mass transfer. You can, this is the ratio of kinetics to mass transfer. When there is a simultaneous kinetics and mass transfer, so certainly if dA is very, very large, which will be dominating? dA is very, very large. Roll number 60, Aditya.
Yes, sir.
If dA is large, so which is my controlling parameter? dA is large.
Sir, reaction rate will be controlling. Reaction rate, sir.
Reaction rate is not controlling. dA is large means reaction rate is fast. This is large,
Yes, sir.
so this will be large. So it will control by mass transfer. If dA is small means mass transfer is large and it will be controlled by reaction rate. If dA is small, is it okay?
Yes, sir.
Okay, so this is Damkohler number. Now, this is clear. So we can get case number 1 from case number 2. Now, what will happen when the reaction is very, very slow? What will be the flux? Mass transfer is very, very large. Roll number 61. Roll number 61, Rutvik.
Yes, sir.
If reaction is very, very slow, what will be the flux?
I think it will be convective.
Reaction is very, very slow, whether it will be controlled by kinetics or mass transfer.
Sir, it will be controlled by kinetics.
So what is the equation which is giving me flux in kinetics?
Flux in kinetics.
Flux in kinetics is given by which equation?
Sir, NSZ is equal to K1 double dash CXN.
Yeah, it is there on a screen. Okay, when the reaction is very, very small, NaZ will be equals to K1 double dash C into XA.
Yes, sir.
C into XA. Can you get this case number 3 from case number 2?
Case number 3 from case number 2. Yes,
now this is what the this case number 3 is there. So this after already we are seeing, after expanding and rearranging, I will get this equation. Okay, if say DAB K1 double dash is small as compared to DAB, so DAB is large. DAB is large means 1 plus DAB K1 double dash delta will be equals to DAB K1 double dash delta. Okay. This 1 will be negligible as compared to this term because the ratio of DAB K1 double dash will be very, very large because K1 double dash is very small, and this is a large divided by very small, that tends to infinity, and that is very, very large as compared to 1. So this term will be equals to DAB K1 double dash delta. Now after substituting this and rearranging and then expanding this using this, actually 1 x ln x equals to 1 minus x, actually you will be getting this equation. First of all, you substitute, you neglect this 1 is neglected, so DAB will be gone, DAB is gone, delta is gone, so you will left with 2c K1 double dash, and this will be ln 1 upon 1 minus 1 upon xa, that will be equals to minus ln half CA0. So that will be a half CA0, you will get half CA0, and that 2 will get cancelled, and you will be left with K1 double dash CA XA0. Anyway, this XA, and so it means that if mass transfer is very, very small, what will be the concentration variation then? What will be the concentration profile if mass transfer is very, very large? If mass transfer is very, very large, DAB is very, very large, then what will be the concentration profile? Here, roll number 62. Roll number 62, Rameshri. Roll number 63, Shreyas.
Hello, sir. Am I audible?
Yeah. If mass transfer kinetics is very, very small, what will be the concentration profile?
Sir, the rate equation will be NZ is equal to K,
No, what will be the
K1 dash.
concentration profile?
Yeah, it will be like ln, sir, because when we will integrate that equation, like it will be like ln.
No, if 100 molecules are coming and only one molecule is reacting, what will be the concentration profile then?
It will be constant then, no change in concentration
it will be
profile.
constant, and everywhere there will be concentration will be equals to Xi.
Yeah.
Because concentration will not change much because mass transfer is larger. Mass transfer is larger, and you are transporting the molecule at much more rate as compared to it consumed. So overall concentration will be constant, and instead of having this, so where is that profile? Here. So this Xa0 will be constant here. So throughout this concentration will be constant, and here rate will be NAZ. NAZ will be also constant, which will be equal to K1 double dash Xa0. So you need not to do rate this shell balance and everything. Just logically itself you can get the concentration profile and flux profile. Concentration profile and flux profile. So that you can use, and accordingly you can get the concentration profile and flux profile for fast reaction kinetics. Okay, this is all about this problem. So what we have discussed is first generalized case and local rate of mass transfer. Then a special case when reaction is very, very fast, and then reaction is very, very small. This is again giving me a local rate of mass transfer. Local rate of mass transfer, we can obtain local rate of mass transfer this multiplied by surface area of catalyst. That will give me local rate of mass transfer. And if I know the length of the reactor, I can assume a steady state for or negligible change in concentration for small delta L, length of the reactor, and then integrate it over, take the mass balance over this delta L, and then integrate it over 0 to L. So I will get overall rate of mass transfer. So anybody has any difficulty over this? Just I will go through this problem. So just looking through all the slides. Just let me know if you have any doubt over this problem on any slide.
Hello, sir.
Yeah. Shreyas,
Sir.
Karthik. Yeah,
Yes,
Karthik,
sir.
tell me.
Sir, can you repeat why in the material balance we neglected the consumption and disappearance term?
We are taking a material balance in the differential shell. Na? Whether reaction is happening here in this differential shell, reaction is happening at the surface. So there is a consumption or consumption and appearance of B at the surface. That is the boundary of my differential shell. That is the boundary of my this film. So in this film there is no consumption. There is consumption happening at the surface.
Yes,
So that consumption and disappearance or appearance of the B is at the surface. So that will be used as a boundary condition.
Sir, and I got this, sir. Sir, other doubt was irrespective of whether we choose Cartesian, cylindrical, or even spherical, we will get the same rate equation and it won't matter. So initial assumption.
You will not get same rate equation.
Sir, but
no, just listen to me. You will get a different equation, but absolute value will be same.
Sir, if we will get the same material balance and ultimately we are getting the rate by multiplying it with
That
flux.
will be in the form of, look, that we have discussed initially also. Model equation even depends upon origin also. Instead of origin, if you are taking origin here, you take a origin here. This is z equals to 0 and this is z equals to delta. So you will get a different model equation. But absolute value, what will be flux at this surface? Flux, say I am getting using one model equation at 20 moles per meter square per second here. So at this point, even if I use Cartesian coordinate system or cylindrical coordinate system, if I am estimating that flux will be 20 moles per meter square per second. Absolute value will not change. Average value, if I am calculating average variation in concentration, that average value will not change. Magnitude and that unit will not change. That will remain same. Equation may change. And this, in fact, we have discussed in detail when we have changed the origin. When we change the origin in that flow over flat plate, you will get a different model equation. You get a different model equation, but absolute values, what do you mean by absolute value? So average velocity that will not change. Then mass flow rate that will not change. And local, say you are calculating a concentration at particular value of x, that will not change. Okay, model equation may change.
Sir, but even if I tried it with cylindrical system, say R, theta, and Z, we are neglecting the variation in R and theta. So again, we'll get the Z variation.
No. There will be variation in R direction.
Oh, okay, sir. Then it's fine.
So theta is equivalent to x, phi is equivalent to y. So this is my surface. Again, I think you are confusing with this figure. This is not approximation of this.
Yes, sir. That's what I initially solved it by wrong Cartesian system, wrong cylindrical system, and I thought I'm getting the right equation.
So that is what I told so many times. Many times, looking at this figure, what people will think that this figure is an approximation of this.
Yes, sir.
But this figure is an approximation of one catalyst particle. This surface is an indicator of this catalyst particle. and this film is around this catalyst particle, and this is giving me local rate of conversion of, still I have not got this actually. What will be the this conversion at this point? That I have not got. I have got local rate of conversion of A to B, that I am repeating so many times. Now if I have this local rate of conversion of A to B, first assumption what I can take is, so radially there is no variation in local concentration, because maybe radially there is, so 5 particles, so this gas molecule is coming in, so radially there is no variation in concentration. Secondly, I can take a small value delta L in length and assume that there is no change in concentration. Take a mass balance over this delta L. Input minus output plus generation and consumption. Their generation and consumption will be there because you have flux. That depends upon how many particles are there in one cross-sectional area. That will give you rate of consumption and generation. And in this differential area, then you will integrate that over a length, so you will get an overall rate of conversion of A to B. Got the point? That second stage I am telling. Second stage we are not covering. For that you need additional information. What you need? What is the packing density of the catalyst particle in a cross section? Number of particles packed. Say if I am considering a small value of delta L. Delta L into, say, cross sectional area is A. Delta L into A volume, that will be differential volume. How many catalyst particles are there? What will be the surface area of that catalyst particle? That will be deciding what will be the consumption of A. That consumption of A will be integrated from 0 to L. Okay?
Yes, sir. Thank you.
Anybody else?
Sir? Excuse me, sir.
For Aditya, tell me.
Yes, sir. Adding to the Karthik's doubt, when he asked you, you said that the reaction is only happening on the surface at Z equals to delta, right? Hello?
Yeah. Yes.
But while making the concentration profile, we are making the concentration profile from the hypothetical stagnant film to the surface. So that's showing the variation of the concentration, right?
Yeah, variation of concentration.
So that's why the consumption and production term should be there, right? In between Z equals to 0 to Z equals to delta.
No. This concentration profile is with respect to Z, not with respect to time. Consumption will be with respect to time.
Okay.
So here concentration will be Xa0 at time t equals to 0. Time Xa, this will be Xa0 at time t equals to infinity. Concentration will be Xa0. There is no rate is with respect to time. That is not with respect to location.
Yes,
so
sir, yes.
You need to say here concentration is Xa0 and here concentration, say Xa0 is 0.8 here and here 0.6. So you mean there is a consumption of A in this. How?
Right, sir. Got it. There is no time variation. We are not talking about time variation here.
Yeah,
right.
we are discussing variation in Z direction. You now you think that you are ignited that agarbatti in your room. This is very common example. Many people will do in mass transfer. At one corner, you are ignited agarbatti, and that smell will come. What is that smell? Smell is some aromatic compound fragrance. So that will initially you will get more smell, and after some time you will get lesser smell. So slowly by the time of evening there is no smell of that fragrance in your room. Whether it means that it get consumed, it is not consumed. It is transported from one place to another place. So it might have spread throughout your hostel. It is not anymore in your room, but it is not consumed.
Yes, sir. The variation with respect to the place, right?
Yeah, this is also exact, and this is the reason why there is a mass transfer is taking place from here to here, because here concentration is smaller. Hence, there is a driving force. Difference in concentration is a driving force, and because of that, mass transfer is taking place.
Yes, I got it. Thank you.
Okay. Okay, then if there is no more questions,